hierarchy scale. And my talk will have two parts. The first part is really a review. I'm going to say some things about the hierarchy problem, and it might be familiar to a lot of you, but I think given the fact that we've discovered the Higgs boson and we haven't yet found any of the hypothetical models that we were hoping would explain electroweak symmetry breaking, I've been hearing more and more people talk about how they think there just is no problem to solve and the standard model is the right theory and we should just pat ourselves on the back and be done. And that's not my attitude. So I want to just review why I think this is an important problem. In the second part of the talk, I'm going to give some interesting examples of TeV scale physics and how we might learn about TeV scale physics. And I'll be advertising work done by some other people, including some students at Harvard. I'll talk about some event-shaped tools for exploring unusual events at colliders. I want to talk a bit about recent progress in electron EDM measurements, and I'll say some things about the Galactic Center GeV gamma ray access as well. Okay, so beginning with the hierarchy problem. In particle physics, a lot of the most important questions that we have to solve are questions about small numbers. And the hierarchy problem is the question of why the weak scale is so small compared to the scale we infer from gravity, the Planck scale, where the ratio of mw squared to m Planck squared is something like 10 to the minus 33. So that's a very small number and we would like to explain it. But there are many other problems in particle physics that are also problems of small numbers. So one good example is the strong CP problem. Why do the strong interactions seem to conserve CP extraordinarily well? The theta term has been constrained to be smaller than 10 to the minus 10, when in principle we might have thought it was an order 1 number. But there are many other problems along these lines. I'm not going to read through everything on the slide, but Yukawa couplings, the cosmological constant, the abundance of dark matter, these are all small numbers. And whenever we see a number that could have been order 1 but turns out to be orders of magnitude smaller, we want to understand why. And I think that's sort of a common theme for many of our most important problems in particle physics. What I want to emphasize is I think that's true whether or not there is a technical naturalness problem. So whether or not we have some sort of power divergence in a loop, we care about these problems, including things like the strong CP problem, where there's no real analog of the divergence problem we have for the Higgs. And the hierarchy between the weak and Planck scales is not just some kind of abstract question of quantum field theory. And the fact that this hierarchy exists is really important for the structure of the world around us. And so I want to remind you of some physics of our universe, which is that we wouldn't have big objects like stars and planets if we didn't have a hierarchy between the Planck scale and the weak scale. So the mass of the sun, if you convert it to units of GeV, is about 10 to the 57. And it's not an accident that that's the cube of 10 to the 19, which is the ratio of the Planck scale to the proton mass. In fact, you can estimate the size of a star by thinking through the physics of what a star is. A star is a ball of hot gas that's hot enough for nuclear fusion to happen in its core. And the physics of nuclear fusion was explained decades ago by Gamow. At some temperature, there's a Boltzmann factor, but there's also a tunneling process. You need to have nucleons get close enough together that the fusion can happen despite their Coulomb repulsion. And these things go sort of differently with energy. And so there's a peak in the nuclear fusion rate when this energy scales in a certain way with the proton mass and the temperature and the fine structure constant. And in order for nuclear fusion to be efficient, you need the temperature to be bigger than alpha squared times the proton mass. Okay, so there's a minimum temperature for an object to have for it to be a star like the sun that's undergoing nuclear fusion. Another feature that you need is there's thermal pressure in this ball of hot hydrogen, and you need that to balance the gravitational attraction that wants to collapse everything. And you also need the star to not be so small that electron degeneracy pressure is important. Then it would be some other kind of object like a white dwarf. And so there's this balance between different fundamental forces. And using that balance, you can estimate the properties of objects like stars pretty simply. If you've never done these calculations before, I really recommend that you look especially at this paper by Weisskopf from 1975, which goes through a lot of examples, not only about stars, but about other kinds of macroscopic structures in the universe and how to estimate them from first principles. But when you go through the estimate for stars, you learn that the mass of a star in units of the proton mass is bounded below by the cube of the ratio of m Planck to m proton. So that's that 10 to the 57 number. It also depends on some order 1 numbers, like the ratio of the proton to electron mass and the fine structure constant, that turn out to kind of, well, this one's a bit large, this one's a bit small, you multiply them, you get something that's order 1. And in fact, a star can't be much heavier than this lower bound or it will collapse. There's similar reasoning that tells you the maximum mass of a rocky planet like the Earth has a similar scaling. It goes like the cube of the Planck mass over the proton mass times something that depends on the fine structure constant. And so if you think about what our universe would be like if we didn't have an electroweak hierarchy, the Higgs bev would be huge. If you hold everything else fixed, the quark masses would be very big. Then the proton would be very heavy. And you just wouldn't have a large ratio here, and you wouldn't be able to form big objects. So the very fact that we can exist and live on a big planet depends crucially on the electroweak hierarchy. So we should really want to understand why this hierarchy exists. Okay. So from my point of view, that's what the hierarchy problem is. It's why is there this large ratio of scales? Can we understand it in terms of something more fundamental where we're not putting in an enormously large or small number by hand? And a good example of an understanding of a hierarchy comes from QCD. We don't worry about this problem for the QCD scale because we can calculate the QCD scale, and we see that if we put in sort of a reasonably small input parameter, which is a gauge coupling measured at some high scale, then there's this well-known phenomenon of dimensional transmutation where we get a small scale out, which comes from an exponential, because the coupling runs logarithmically over many decades in energy and gradually becomes large. And similar things happen in condensed matter physics. So there's a very similar understanding of superconductivity in the BCS theory as coming from some marginal coupling that gradually runs to be strong and produces a hierarchy of scales. And so we would like to have a similar understanding of the electroweak hierarchy, not necessarily literally the same. There was an old theory called Technicolor that was basically literally this formula, and we know that theory is wrong. But we would like to have the same kind of qualitative understanding where we can put in some order 1 inputs and some dynamics and understand how we got a very small number out. Another thing I want to emphasize is people often talk about the hierarchy problem in terms of some kind of fine-tuning measure. If you vary some input parameter, how much does the weak scale change? And if you do that estimate for the QCD scale, you find that there's this moderately large sensitivity. If I vary the gauge coupling in a high scale, this exponential changes. And so some typical measure of fine-tuning, like the Barbieri-Giudice measure, might tell you the QCD scale is tuned by a factor of 100. But we don't really worry about that because the robust fact is that we put in modest numbers and we get out an exponentially large separation of scales. Exactly what that separation of scales is depends on exactly what your inputs are. But still, that's a reasonably good understanding, and we should be happy if we have a similar kind of understanding of the weak scale. So the question about the weak scale is really, where did it come from? And there are various refined versions of this question you could ask. Can we explain or compute the weak scale in terms of some more fundamental theory? Can we understand some dynamics that told us electroweak symmetry breaking was more likely to happen than not? What is the shape of the Higgs potential? That's a strong motivation for future colliders to go and measure the Higgs self-coupling, which we really need a high energy proton-proton machine above LHC energies, or some machine like the ILC that can collide electrons and positrons at very high energies in order to get really accurate measurements of that. The LHC will give us a first glimpse, but we really want something more accurate. Relatedly, is the Higgs fundamental or composite? What's the shape of the potential, not just at 0 temperature, but at high temperature? What happened in the early universe? These are all questions that I consider part of this challenge of understanding the electroweak hierarchy. What I want to emphasize is that what I don't consider to be the main question is anything about how to regulate loop diagrams. The thing that I'm calling the hierarchy problem would not go away if you tell me that your favorite regulator is dimreg and it doesn't have any power divergences. It wouldn't go away just because we pick different choices of how to measure fine-tuning. And the fact that the standard model is a renormalizable theory and we can measure some input quantities and then calculate everything else to high precision and match data does not mean that there's nothing to explain, because the question is really about the origin of these parameters, not just about how we use them to do calculations. And I think the reason why there's been sort of a wave of people saying that they don't really believe the hierarchy problem is a problem is because it gets mixed up with some of these issues about how to calculate loops. Certainly in the past, I've given talks where I've shown this kind of loop diagram of a loop of top quarks coupling to the Higgs, and I've said this introduces a shift in the Higgs mass parameter, which goes like a quadratic cutoff squared. And that's something where if you say that, then you might hear people respond, well, power divergences are not really physical, they're an artifact of your regulation scheme. Or if you would just measure the Higgs mass and use the renormalized mass in your calculation, you wouldn't have any problem. And those things are true, but they're not really getting at the heart of the problem that we worry about. Okay, so we should be careful how we describe the problem and not just describe it as a problem of quadratic divergences. And sometimes we're maybe more careful when we talk about the problem in the context of some theory, like, for example, supersymmetry, where the Higgs mass can be calculated from some input parameters like the soft SUSY breaking masses, the mass of the stops which run in loops. And there we see formulas that don't have those power divergences. This is a formula that would look similar whether we talk about dim-reg or any other regulator. We have logarithmic sensitivity to a cutoff, but we have quadratic sensitivity to actual physical scales. And so that's something more physical that we can worry about. But to get to that point, we had to embed the standard model in a bigger theory. So the way that supersymmetry solves the hierarchy problem is something like this. Imagine that we could have supersymmetric parameters, masses of scalars that are somewhere in the TeV to 10 TeV scale, for instance, and we vary some other parameters. We vary maybe the top Yukawa, the B term. We could vary these parameters too, but I can only show you 2 dimensions on a plot. Then you can just calculate the weak scale. You can calculate what is the Higgs dov as a function of these input parameters. And here I've just done the calculation for some parameters, and you find that when you put in TeV scale inputs, you get TeV scale outputs in a lot of the parameter space. Beyond some critical boundary, you might get something else, like there's a flat direction you can run out along and get very big dovs. But if you tell me that we live at a point here, and I look in some neighborhood of the point and I see typically the same order of magnitude for everything near that point, I would say, yeah, you've solved the problem, if that matched experiment. And so fine-tuning only comes in at some higher order stage where you start worrying about, is this solution robust? When I look in some neighborhood of a point, do things vary a lot or a little? If we found ourselves living near this boundary, we would conclude that things are fine-tuned. And that would mean that this wasn't such a good solution. And indeed, it seems like supersymmetry is not as good a solution as we might have hoped. But there's still a chance that the fine-tuning is modest and that maybe it's a close enough solution. But I want to emphasize that the problem is really, where did the weak scale come from? Can we calculate it from some underlying theory? And the fine-tuning is sort of a higher order thing. And the fact that we've been talking about it, sometimes putting the cart before the horse, I think has led to this kind of backlash you hear in some corners of the community where people say there's nothing to explain. Final comment about the hierarchy problem. I think we shouldn't over-rely on the notion of technical naturalness. As I said, I worry about things like the strong CP problem. In my mind, that's a problem that's as important as the hierarchy problem. It's probably an important clue to physics in our universe and maybe to the nature of dark matter. But it's not a power divergence in the same way. But it is the same kind of problem of there's a very small number and I want to know where it came from. Now, if you have a theory that's technically natural, that means that there's some small number that when you calculate loop corrections remains small. And that's a good thing for a theory to have. You want an explanation of a small number to have that property. But a theory that has that property may not be a solution to the problem if you just put in a small number by hand and didn't say where it came from. It's maybe a step along the road to a solution, but not a full solution. And so I think there's maybe a tendency to build models where technical naturalness is the end of the story, and I think it should be the beginning of the story. And indeed, there's a whole other talk that I could give you that I'm not giving you today about things like the weak gravity conjecture and things that we learn when we look at UV complete gravitational theories, where it seems like anytime you find a very small number, if you're not putting it in by hand, but you're getting it from a UV complete theory, there's a host of other consequences that comes along with that. Okay, so that was the first half of the talk, just trying to convince you that it's still important to think about TeV scale physics and where the electroweak hierarchy came from. In the remainder of the talk, I want to talk about some examples of how to think about TeV scale physics. And the first thing I want to talk about is something very practical for thinking about how we analyze data at the LHC, which are new ways to characterize events. If we're trying to find something that's buried under huge backgrounds, it's always useful to have new tools that give you new insights on how to distinguish different types of events. And the tool that I want to mention today is the energy mover distance. This is something that was introduced recently by Patrick Comiskey, Eric Metodiev, and Jesse Thaler at MIT. It's a variation of something that's been called the Earth mover distance in other contexts. And it's basically given two events, you ask, if you sort of pick up energy deposits in a calorimeter and move them to some other place, how much does it cost to rearrange one event to look like the other event? And so you pay a penalty that's basically a product of how far you moved something from one cell to another, times some weight. That's how much stuff did you move, how much energy do you have to shift around to make one event look like another event. So this can generally be a useful way of kind of characterizing how different two events are from each other. And it has many applications, but one application I want to highlight is work by my student, Carrie Cesarati. She gave a parallel talk on Monday, so you can look at her slides for more details. And that's a particular application where you get a measure of how spherical an event is by starting with some reference event like the one shown that's very spherical. So you sort of tiled a sphere with equally positioned energy deposits. And given your event, you can ask, how much do I have to move things around to make it look like a sphere? Okay, so why is that interesting? It's interesting because we know that there are theories that are not QCD-like that can generate very spherical events. And a canonical example is strongly coupled N=4 super Young-Mills theory, where Strassler conjectured and Hoffman and Maldacena showed that event shapes in that theory are perfectly spherical when you go to the large Tiff coupling limit. There are discrete analogs of that in various kinds of hidden valley theories. And so a very simple way to generate these events is to start with a 5-dimensional model, sort of a Randall-Sundrum-like toy model of a hidden valley, make some heavy Kaluza-Klein mode and let it cascade down, and you get many daughter particles, and their momenta can look like this picture. They can be coming out in many different directions. And so what Carrie and I and Matt Strassler are currently working on is using these kinds of events as sort of a test case to play with this event isotropy variable and see what it can buy us. And what we find is that it gives us useful information that's different from traditional variables. So here's an example of a 2D plot where the vertical axis is an old-fashioned event shape variable called thrust. When thrust is large, we have jetty events. When thrust is small, we have events that are very far from being dijets. And the horizontal axis is this event isotropy variable. When it's 0, that means you have 0 distance to a spherical event, so your event is very spherical. When it's 1, your event is very non-spherical. So dijet events would end up in the top corner, spheres would end up in the bottom left. And we see that we have these different toy 5D models. If we have a bulk interaction, it turns out the preferred decays are those that have very small phase space because they approximately conserve some sort of Kaluza-Klein number. And so you get these events that are pretty spherical. If you put an interaction on the boundary, you have events that are more determined just by pure phase space decays. And so often decays go to very light daughters and they produce very energetic things. And those give you boosted objects that look more like jets, and you end up more up here. And then there are interesting things that happen when you have multiple fields and the wave function overlaps become complicated, and you get these sort of islands of large branching ratios in other regions of the daughter masses. And what I want to emphasize, there's a lot of detail on this plot, but the thing to notice is just, if we only had old-fashioned variables like thrust, there could be substantial overlap between some of these distributions in some regions. When we use the new variable that Carrie and Jesse invented, these regions start to separate from each other. And so this new variable is giving us some new handle on events that we didn't have before. And I think it's important that we keep thinking about new ways to analyze LHC events and apply them to the data so that we can hopefully find some unexpected things. Okay, so that was one topic. Another topic about TeV scale physics, or even physics at energies a bit above the TeV scale, is searches for CP violation. Here I want to emphasize some really excellent work that's being done by atomic physicists. So colliders might not be our first discovery of physics at the TeV scale beyond the standard model. And in particular, there's been really dramatic progress in attempts to measure electric dipole moments, and especially in the electron electric dipole moment, although I think we're going to see improvements in hadronic EDMs as well in the near future. In particular, there was a new result from the ACME2 experiment. The PIs of that experiment are Dave DeMille, John Doyle, and Jerry Gabriels at Yale, Harvard, and Northwestern. And they use a polar thorium monoxide molecule that passes through some apparatus. They sort of zap it into a particular state with a laser and then watch for it to decay. And they have external E and B fields they can apply, the E field to polarize the molecule, the B field to give you some precession of the spin. And they can do a very accurate measurement and infer whether or not there's an electric dipole moment. And the bound they set is 10 to the minus 29 in these funny units of E centimeters. To a particle physicist, we would like to translate that into some kind of mass scale. How heavy is the new physics they're probing? And we can do that with a simple estimate. The EDM violates chirality, so it's always proportional to the electron mass. It's inversely proportional to 2 powers of some heavy mass scale that comes from a dimension 6 operator. And then it might come from some loops, so there might be some loop factors in front. And of course, it depends on how big your CP violation is. But if we assume there's an order 1 CP violating phase, we can translate what they're doing and say, well, I don't actually know any model that does this at tree level. But if I put in this estimate at 1 loop, they're probing new physics at kind of the 50 TeV scale, well above what the LHC can probe. And in fact, even if the EDM is generated at 2 loops, they're probing new physics at the scale of a few TeV. So they're really making substantial progress and telling us about things that are at high energies that we have not yet been able to reach at colliders. And here are some example plots of interpreting that number in the context of some models. So this was work with my students, Kerry Cesarati, Chen-Chu Lu, and Aditya Parikh, as well as a postdoc, Yuichiro Nakai. And let me just talk about the left plot on split SUSY. The right plot is where you also make the gauginos heavy. But basically what you see is if you have heavy scalar masses in supersymmetry, you're going to tend to overpredict the Higgs mass, make it too heavy. So there's some kind of finite region that you want to explore where the masses are not too heavy. And what these blue contours are showing you is the EDMs are pushing into a large fraction of that region. So a lot of the parameter space for split SUSY, these are 1 loop effects of the scalars that we're probing. And assuming the squarks and leptons are all at the same scale, you can play games where you separate them and move things around a bit. But basically a large part of the parameter space of split SUSY, if there are order 1 CP violating phases, is being probed by these EDM experiments. And at 2 loops, there are also important effects that come from these bar Z diagrams with charginos running in an inner loop that are connected by electroweak gauge bosons and Higgses to the electron. And this is probing chargino masses of order a few TeV. That's the blue contour here. For reference, these orange contours are direct detection results from xenon 1 ton if the neutralino is the dark matter. And so you can see they're very complementary to each other. They're probing similar parameter space. The EDM bound only applies if there's CP violation. The other bound only applies if this is dark matter. So neither one is completely universal, but they're both cutting into substantial parameter space. And what's really exciting about this is that there are future experiments being planned that are going to significantly improve the bounds. So to improve the bounds, you need longer coherence times or more molecules or both. And these bounds were done using some diatomic molecule, thorium monoxide. And the reason for that is it has what the atomic physicists call an internal co-magnetometer. Basically, it has states that come in some sort of doublet that get shifted in opposite directions by some effects that let you cancel off some systematics. And this gives them a very powerful probe of CP violation, where they can remove other effects that might produce similar signals in their experiment by taking the right combinations of different things they can measure. It turns out the molecules that are good for that are not necessarily good for producing large numbers of molecules, which can be done with laser cooling. Laser cooling of molecules is harder than laser cooling of atoms because there are too many modes in the molecules. There are all these rotational and vibrational modes that get excited, and you don't want to excite them. And so what's recently been proposed by Hutzler and Kozyriev is that there are polyatomic molecules that have the right structure that you get both properties you want. There's sort of one part of the molecule that your laser can latch onto and cool. There's another part that gives you the co-magnetometer that you want to control the systematics. And it seems like all the aspects of this are understood and under control. And they project that within 5 or 10 years, they can do an experiment that will improve the bound on the EDM by 3 orders of magnitude. And we said that the EDM depends quadratically on the mass scale of heavy new physics. So this is basically giving you a factor of 30 improvement in the mass that you reach. And that's probing 1 loop particles all the way at the PeV scale, 1000 TeV. And there are several other competitive experiments that are happening at the same time using different kinds of technology. And so I think people have made big promises about EDMs in the past, and for a while the progress was kind of slow, but I think now there's really a lot of indications that people really know what they're doing, and they're going to be improving these bounds rapidly for some time to come. And that's very exciting, and we should think about what these bounds will mean for particle physics. So to give you one example where I put that in some context, I can talk about the galactic center GeV excess. So this is the excess of gamma rays in the galactic center that was discovered by Goodenough and Hooper about 10 years ago. And many other people have followed up on investigating this data and trying to understand it. I've probably missed a lot of people, but I've tried to name some of them here. The big question about the GeV excess is it coming from dark matter that annihilates and produces standard model particles? Thanks. And gives us gamma rays that we can see, or is it coming from some traditional astrophysics like millisecond pulsars? And 5 years ago, it seemed like all the evidence was tilting toward point sources and millisecond pulsars. And there's an ongoing debate. I'm not going to try to judge which claims are the most plausible, but I think it's fair to say that at the moment, if you look at some of these recent papers, some of the evidence for point sources that people were advocating 5 years ago has been questioned, and now the dark matter possibility is more alive than it seemed to be. And so it's worth thinking about. Now, if you're a model builder and you want to explain this, you can think about various kinds of models that might do this. One example could be dark matter just directly annihilates to standard model states. For example, it could couple to the Higgs boson, and then it will often produce BB bar, and that turns out to fit the data well. That gives you a good spectral shape. You could enhance the signal if the dark matter mass is close to half the Higgs mass, so you could lie near a resonance. But still, it's hard to fit the rate if you just add a CP conserving coupling here, because if you have two non-relativistic Majorana fermions that are annihilating with each other, that's a CP odd state. The Higgs is CP even, and so so there's a velocity suppression that comes with this process. But that's not true if you have a CP violating coupling here. On the other hand, if there's a CP violating coupling, you should worry about the EDM bounds that I was mentioning before. So we have very strong constraints on CP violation. Two loop effects can feed them into the electron EDM, and that's something you might worry about. On the other hand, there's a very different class of models where dark matter annihilates to some mediators. Maybe they're dark photons, maybe there's some sort of scalar. But if those are on shell, they can kind of hang around for a while and then later have the second step where they decay to standard model particles. That kind of model decouples the annihilation rate from the standard model coupling, which means you can easily evade lots of terrestrial experiments that might constrain your model. And there are various models along these lines that fit the shape. Okay, so it's not hard to build models that fit the galactic center excess. But I think there's a very interesting question, given that we think the Higgs is important, of can you do it with this first kind of model? And there I want to mention some nice work by 3 students at Harvard, Katie Fraser, Aditya Parikh, and Linda Xu. Linda gave a parallel talk on this on Monday, so you can see her slides. There was also some related work last year by Karina, Osborne, Shaw, and Wagner. And what they do is they take a model where you have 2 fermions, a singlet and a doublet. They mix through Yukawa couplings with the Higgs. They have a CP violating coupling, so that can give you this annihilation signal. And here they're checking various bounds, spin independent and spin dependent direct detection, the EDM, getting the right annihilation rate. And the white region is some region that's allowed by the data. And the reason it's allowed by the EDM is the singlet doublet model doesn't have the bar-Z diagram I showed you before, which is very constrained. It only has this other one where you have 2 W's connecting things to the electron, and you have a neutralino in the loop, or a neutral fermion. And it just turns out, kind of for some numerical reason, this particular diagram happens to be smaller than those other 2 loop diagrams that I showed you that were giving very strong constraints. And so the singlet doublet model still has viable parameter space as long as you don't have other charged particles that are mixing in, as long as they're heavy enough. But the exciting thing is these EDM bounds are improving rapidly. And so if something like this is explaining the galactic center excess, as this EDM contour improves, it's going to push to the left and probe this white region. So there's really strong motivation and strong interplay between these atomic physics experiments and other things we care about in particle physics, including possibly the nature of dark matter. Okay, so I'm about to wrap up. I just want to make this comment that even if, imagine these atomic physicists do a really great job with these experiments and they discover that there's a non-zero EDM. These experiments have very good control of systematics. If they make a discovery, it can be decisive. We would really know that there's new physics. However, all we would know is the coefficient of one operator or one linear combination of operators beyond the standard model. We wouldn't really understand the source of that new physics. So if we really want to thoroughly understand new physics, even though there are all these other experiments that are fantastic, we really need a collider. And so I think the future of our field is really going to require us to build a big tunnel. Maybe initially it'll host a Higgs factory, but at some point we're going to want a big tunnel to host a new energy frontier machine. And whether it's near Geneva or near Qinhuangdao or somewhere else entirely, I think we need that for our future. Okay, so to summarize, we found the Higgs boson. It looks like an elementary spin 0 Higgs, but we really don't understand the weak scale, and we need to keep trying to understand it. So we should make the best use we can of the LHC using the best tools that we have and inventing new tools. But we should also be planning for the future. And when we do that, we really should emphasize these big picture questions like the hierarchy problem. to motivate physics at this scale. We should keep an eye out for discoveries beyond the world of colliders like EDMs and dark matter. But we really need new energy frontier colliders, and I hope that that's what we have in our future. Thank you.
Great, thank you for a really interesting talk. We have a couple questions in the Q&A. First question comes from Carlos, who says that, I agree with your emphasis on physical regularization independent effects. One issue is that once you abandon the concept of quadratic divergences present in the standard model, it is difficult to explain the special role of the Tapiocawa. This special role is reintroduced in theories like SUSY or extra dimensions, where there is a connection between couplings of particles and new physics patterns, but in general, it does not seem to be there. Can you comment on this?
I think that's a fair statement. So as I said, I think the problem really shows up when someone tells you they have a theory that can explain the weak scale, like supersymmetry, for instance. And where the fine-tuning problem comes in is within that theory, you can ask, is it robust? As I vary the parameters, do I have sort of something stable, or am I sitting very near some critical boundary for no apparent reason? I guess all I can say is I agree with what Carlos says. In any particular theory I know that does that, it's usually some correction related to the Tapiocawa that's extremely important. And in some sense, this heuristic argument that the Tapiocawa and the quadratic divergence matters has a form that's actually true in those theories. What I can't say is that I know that there's not some completely different kind of solution to the problem where the Tapiocawa doesn't play a role. Yeah, maybe something more exotic, some relaxion scenario or something, the Tapiocawa is not going to be so important, and it still might give us some solution to the hierarchy problem.
Great. Our next question comes from Lian Tao, who wants to know, in the doublet singlet model, does the existence of the GCE need CP violation?
Good question. Yeah, so I think the right statement here is that it's possible to fit without CP violation if you tune extremely close to the resonance. I'm not completely sure of the numbers offhand on this, but I think it works. That the Higgs width is small enough that if you're willing to do a lot of tuning of the mass so that you sit right on the resonance, then maybe you have a big enough annihilation rate even without CP violation. Although I'm not sure if you can completely evade other bounds. So I guess the answer is I don't completely know, but I think it might be possible. But here it's a lot easier to evade the bounds if you have the CP violation.
All right. We have one more question from my colleague Antonio. You did not mention a lot about dark matter. Can you comment on the possible connections of dark matter to the weak scale?
Well, I guess I did mention a few things about dark matter here. I think, if it turns out that we have a signal of dark matter like the galactic center excess and that we can relate it to the Higgs, that would be very intriguing, but it wouldn't necessarily tell us why these scales are related. Right, there's some mass scale for these fermions, which a priori is unrelated to the weak scale. In the context of something like supersymmetry, of course, there's a reason for them to be related. And in the context of lots of other models like neutral naturalness, there can also be dark matter candidates where there's a good reason for their mass to be related to the weak scale. So I guess, I don't know, I think there's a reasonably good chance still, even though a lot of WIMP parameter space has been eaten up by experiments, there's still surviving parameter space. And it may turn out that dark matter is related to the weak scale. It may turn out that it's something totally different like axions. I don't know if I have any better answer than that.